Hello, everybody. Welcome to today's webinar, Sewer Thermal Energy for Grid Decarbonization. My name is Twyla Neely-Strite, and I'm the Education and Operations Associate at Illinois Green Alliance. Today's program was put on by the Illinois Green Alliance Programs Committee, a volunteer group that coordinates education events covering a wide range of topics throughout the year for the green building industry. The team that organized today's event consists of Kate Anderson, Damon Henriksen, and Sydney Van Kuren. You've all been muted upon entry, so please type any questions you have throughout into the Q&A function at the bottom. We'll get those answered at the end. This webinar is being recorded and will be sent out to all of you in a follow-up email. So for those who are unfamiliar, Illinois Green Alliance is a membership-driven nonprofit organization that advances green buildings and sustainable communities for all. Our 5-year strategic plan pushes the green building industry to meet or get on the path to net zero. We achieve this work through education events such as panels and building tours, by engaging communities and partnering with organizations across Illinois, and by advocating for new policies and legislation. Members can view our recorded webinars on our on-demand webinar library. You can also learn more about membership and see upcoming events and get involved by visiting our website, illinoisgreenalliance.org. Today's webinar is approved through AIA for 1 LU credit and can be logged for 1 LEED AP or Green Associate CE hour. Certificates of completion for both AIA members and non-AIA members are available upon request. To request AIA CE credit or a personalized certificate of completion for architecture license CE reporting purposes, follow the QR code on your screen and complete the linked form. I'll also be linking the form in the chat, and you can access it that way as well. So for those interested in self-reporting CE hours for your LEED AP or LEED Green Associate credentials, we'll also be sharing self-reporting instructions and a fillable certificate of completion in our follow-up email to all attendees next week through Eventbrite. And here are today's learning objectives. I also want to take a moment to recognize Illinois Green Alliance's sustaining sponsors who make our work possible. A special thank you to our gold level sponsors, ComEd, USGBC, and Sloan. You can make a commitment to advancing green buildings in communities across the state by visiting illinoisgreenalliance.org/sponsorship to start a conversation about sponsor partnership today. And now I'm going to hand it over to Damon Henriksen to introduce our speakers.
Hi, everyone. Thank you for joining us to discuss sewer thermal energy. Today, we have a great lineup of speakers. They will walk us through the process of water reclamation, illustrate how that system can be harnessed to assist in geothermal heat exchange, and touch on the technical aspects of the mechanical systems. I will now introduce our presenters for today's webinar. First, we have Justin Brown. Justin is a senior public affairs specialist at the Metropolitan Water Reclamation District of Greater Chicago, also known as the MWRD. He has a Bachelor of Fine Arts in Visual Communications from the School of the Art Institute of Chicago and is an FAA certified drone pilot. Lastly, he specializes in communicating technical information to a general audience and building public engagement. Next will be Nancy Kohout. Nancy is a senior principal and mechanical engineering leader at SmithGroup, one of the nation's premier architectural and engineering design firms. She has more than 20 years of experience in the building design industry across a range of building sectors. She is currently president-elect of the Illinois ASHRAE chapter and was chair of the first ever Woman in ASHRAE Leadership Symposium this September. Nancy is also a TAM, Technical Account Manager, for the Department of Energy's Better Climate Challenge, helping large-scale portfolio owners strategize to meet their greenhouse gas emission reduction goals. And finally, we'll have Ulrik Folkeman. Ulrik comes with an experience of more than 25 years at a public Danish utility, where he has held positions as both manager and operator. Furthermore, Ulrik has trained staff on different utilities in Denmark in operations and process optimization of wastewater treatment plants and collection systems. He has an in-depth understanding of what it takes to run a wastewater treatment plant, a thorough knowledge about limiting the climate impact of the sector, and of course, how to get the heat out of the water. So without further delay, let's go to our speakers. First one is Justin Brown.
All right, thank you, Damon. The Metropolitan Water Reclamation District of Greater Chicago, or MWRD, is a government agency, and we're responsible for treating wastewater for the Chicago region. We serve an 882 square mile area with 5.2 million people living in it. We have 7 wastewater treatment plants, and we clean about 1.2 billion gallons of sewage a day. I'm going to give you all a high-level picture of the wastewater treatment process, and we'll also take a look at how sewer systems work. So let's, without further ado, jump into that. If we look at early Chicago, Chicago was built on wetlands in a flood-prone landscape. This is an illustration of Chicago in 1820, and if we zoom in here, you can see some areas where the river is sort of advancing into the landscape. These are areas of potential flooding. Chicago began work on a sewer system in the 1850s. This map shows the beginnings of that sewer system. Chicago's sewer system was designed to do 2 things: to carry rainwater into the river to help prevent flooding, essentially, and also to carry raw sewage straight into the river. Now, this was done because wastewater treatment technology did not exist at the time that the sewer system was built. And this is how sewers were built all around the world. They emptied raw sewage into water bodies because there was no way to clean it. And here's a picture of what that looked like. This is the 39th Street sewer emptying into Bubbly Creek, which is a small tributary to the south branch of the Chicago River. Here's another view of Bubbly Creek. Again, this is the result of raw sewage going straight into the river. This is what you get. Now, here's a picture I took of Bubbly Creek a few years ago, and you can see it looks way different. And the difference is today, sewage comes to our plants to be cleaned, and we release clean water to the river. I mentioned a second ago that the technology didn't exist to clean sewage when the sewer system was first built. Well, we actually worked to develop wastewater treatment technology at pilot plants like the one you see here. So these facilities, we prototyped ways of cleaning sewage, figured out what worked and what didn't. Once we learned how to clean wastewater and began work building treatment plants, we also had to get the water to our facilities to be cleaned. So to do that, we built a system of huge intercepting sewers to catch the water, to bring it to our plants. And these sewers are as large as 27 feet in diameter. This is a photo of construction work on one of those intercepting sewers in the 1930s. Today, we have hundreds of miles of these intercepting sewers that carry sewage to our 7 wastewater treatment plants, where we clean 1.2 billion gallons a day. Our Stickney plant is our largest plant, and it's actually one of the largest sewage treatment plants in the world. This plant has the capacity to clean 1 million gallons a minute. I took this picture from about 2,000 feet up in a helicopter, and you can see there's those little specks in the lower left there are cars in the parking lot. It's a huge facility. I'm going to walk you through the wastewater treatment process really quickly and show you some up-close views of how these things look so you can get a good picture of it. Those of you who attended the in-person tour of our Kirie plant yesterday, some of this will be familiar to you, but I'll include some views of some of our other facilities, and hopefully it'll be interesting. So the water has been flowing downhill by gravity through the intercepting sewer system when it gets to our wastewater treatment plants. And the first thing we need to do is pump that water up to the surface to be cleaned. So we have huge pumps to do that. Before we let the water go into our very expensive pumps, we send it through bar screens, which are basically like a large metal fence designed to remove any large debris that could damage the pumps. And over the years, we have removed some interesting objects, including one time a few years ago, we received 2 live opossums. And we were able to safely remove them, and they lived happily ever after on the grounds of our treatment plant. Sounds like maybe there's a children's book in there somewhere about that. People ask, yes, we sometimes even find money on the screens, and a guy that I work with who I totally believe tells me he once found $100 on the screens at one of our plants. So you never know where your money's been. All right, I'm gonna show you what some of this looks like up close here. This is a couple intercepting sewers flowing into our Kirie Water Reclamation Plant. This is the 8-foot diameter Salt Creek interceptor. This is a 17-foot diameter interceptor. This is our west side #1 sewer. This sewer serves downtown Chicago. So if you've ever flushed a toilet in downtown Chicago, you have used this sewer. We're about 50 feet underground here. This is a view that you would never get to see in an in-person tour of our facilities. We don't let the public in here, so enjoy this exclusive virtual tour view. Since we're looking at sewer thermal energy today, we characterize all the water entering our facility. So we test a whole ton of parameters. All that information is available on our website if you're curious. But regarding temperature, the water coming in here varies from a low of the low 50s to a high of just about 70 degrees. So it varies somewhat through the year, and the average is about 62 degrees, the water coming into the plant. These are the bar screens. This is where we remove bowling balls and opossums and $100 bills. Actually, we get a lot of these flushable wipes here. They do not cause a problem for our facilities. We're perfectly set up to scrape those off the screens. We throw them in a dumpster and they go to a landfill. However, we do not recommend that you flush flushable wipes down the toilet in your home. They can cause plumbing blockages. This is the pump and blower building at our Stickney plant. Notice the pumps are well down below ground level. They're down at the level of the sewer. Behind my head are soundproof boxes that hold blowers that we use to provide compressed air for a biological process that we'll see in a second. Running the blowers, we run the blowers using super powerful electric motors that actually account for 50% of our electric bill to run these. And these motors are so powerful that when we're going to turn one on, we actually have to call ComEd, the electric utility, and let them know that we're turning one on, because they'll see the electric grid like dip a little bit. So from here, the first main part of the process is primary treatment. In primary treatment, we let the water sit still, and fats, oils, grease, and plastic all float to the top, and that's all scraped down to one end of the tank. Meanwhile, underwater, organic solids sink to the bottom, and those are scraped out an opening in the bottom of the tank and go to a separate solids process. In primary treatment, just by letting the water sit still, we can remove 70 to 80% of the solids in the water. So it gets pretty clean in this stage. And you can see here, notice how clear this water is leaving primary treatment. It's not totally done yet, but it's interesting to think about. If you're thinking about energy efficiency and cleaning 1 million gallons a minute, you want to use an efficient process to get as far along cleaning the water as you can. The solids go to a separate solids process in anaerobic digesters. There's a biological process in there that produces biogas that we use to heat and cool our plants. In addition to that, the process in the digesters breaks the solids down, so they're now designated by the US EPA to be biosolids, and they can be used as a soil amendment for landscaping. Okay, we're going back to the water stage of the process here. Actually, let me I'm gonna hop back out and show you something here. So water leaves primary treatment and goes into secondary treatment. Secondary treatment consists of aeration tanks and final settling tanks. And the aeration tanks work just like a fish aquarium, where you have air bubbles going into the water. In the case of a fish aquarium, you're aerating the water to provide oxygen for the fish to breathe with their gills. At a wastewater treatment plant, we aerate the water to make the conditions right for beneficial bacteria that help us clean the wastewater. All right, I'm going to show you a highly technical microbiology diagram here. I promise I will explain this. All right, so this is the water entering secondary treatment. There are a few things here. There are dissolved solids, which is the general background color. There are some suspended solids, the little floaty chunks. There's also a mix of naturally occurring microorganisms in the water. There are beneficial bacteria that are harmless, and there are also some pathogens or germs in the mix. And you guys can figure out which is which. So now when we add air to the water, it increases dissolved oxygen, which the beneficial bacteria are aerobic organisms, meaning they thrive in the presence of oxygen, just like us. So when we oxygenate the water, they start moving around, consuming pollutants and reproducing. Now we're flowing along through the aeration tank. Notice that the water is getting cleaner. The good guys are getting more numerous here. The pathogens or germs tend to be anaerobic organisms, meaning they thrive in the absence of oxygen, and in some cases oxygen is actually toxic to them. So they actually get outcompeted for food and they tend to die off. Our microbiology lab pulls samples and we confirm that this is occurring. So now we're at the end of the aeration tank here, and the bacteria that we set up our process to grow have a behavior called flocculation. And what happens is when they run out of food, they go dormant. And when they go dormant, they form little clumps. And once they've clumped like that, they're able to sink and settle out. And this is what occurs in the second part of secondary treatment, the settling tanks. So they settle to the bottom. From here, we let the top inch or so of water flow out of this tank. And meanwhile, about 95% of the beneficial bacteria that have sunk here are sent back around to the beginning of the aeration tank to work again. So let's take a look at these aeration tanks that we just saw the sort of cartoon view of it. Here's what they look like in real life. At our Kirie Water Reclamation Plant, we have 36 acres of aeration tanks. There are 4 pass tanks, so the water zigzags through them 4 times. There's an equal area of tanks on the other side of that tree line there. It's really a huge area dedicated to this biological process. All right, we're looking at acres of churning sewage, and it's about lunchtime. I think all of you would like to see what it would look like underwater in one of these tanks, right? Let's take a look. I put a GoPro underwater in an aeration tank, and this is how it looks. Now, what is interesting here is this water is opaque. You can't see through it. Whereas the water in leaving primary treatment, we saw just a second ago, it was more or less transparent. So why is the water in the next stage of the process dirtier looking? Well, what we're actually seeing here is that this water is saturated with beneficial bacteria. So we've got a really healthy microbiome at work here cleaning the water. So following the aeration tanks, water goes on to final settling tanks, and this is where the flock particles settle to the bottom, and we let the top inch or so of water flow out of the tank. At our O'Brien Water Reclamation Plant, our discharge permit requires us to disinfect the water during months when recreation is likely on the river. We do that using an ultraviolet disinfection facility. In this facility, we send the water through these arrays of super powerful, super expensive ultraviolet bulbs. These bulbs are about $700 each, so you don't want to accidentally drop one. The UV light here disinfects the water before it's discharged to the river. This is a view of the outfall of our Egan Water Reclamation Plant, which discharges into Salt Creek. It's down at the end of this channel here. When I went to this location to shoot some video of it, I was happy to see there were some folks here fishing, demonstrating the thriving aquatic habitat. I was there for maybe 15 minutes or so, and they caught several fish during the time I was there. This guy's pulling out a bass of some sort here. So that is our wastewater treatment process in a nutshell there. I will stick around. If you have questions, please put them in the Q&A section, and maybe we can answer them at the end. So with that, I am going to pass it on now to Nancy.
Well, thanks, Justin. I think that's such a fascinating presentation. And I will say to the group, I don't have any amazing videos like that, but hopefully I'll make up for it with pretty pictures. So just to kind of share with the group, I work for SmithGroup. It's an architect and engineering firm. And today I'm going to share with you one of our projects that I really feel required this sort of integrated expertise all at the table to make happen. Pretty trailblazing project. So next slide. And I would be remiss if I didn't just share a little bit about our firm. We have 20 offices across the country, and we have just fundamentally a value system of sustainable design, and really excited about what's happening in the landscape of decarbonization these days. So excited to share our project with you. Next slide. So just to understand kind of the value of wastewater heat exchange, I want everyone to just take and I know my audience doesn't have all engineers, so I'm going to give this a kind of a very basic explanation. When we talk about electrification towards decarbonization, we are talking about heat pump technology. And heat pump technology uses the refrigeration cycle to move heat around. So instead of saying like, oh, we need to, use electricity to make heat, which would be like 1 unit of electricity makes 1 unit of heat, we're talking about using heat pump technology to move heat around, which is more on the order of 1 unit of energy moves 3 units of heat. And when we start to look at things like simultaneous heating and cooling and water source heat pumps, that 1 to 3 could be more like 1 to 5, 6, or 7. So there's this a great opportunity to get our existing power infrastructure that we have, especially in cold climates like ours in Chicago, to function with heat pump technology. And water source is very key. I'm going to explain a little bit about why that is. Next slide. So we know, we hear the term heat pump all the time, and sometimes we have, we can buy condensing units for our, home air conditioning that have heat pumps. They reverse the refrigeration cycle, but they struggle because as the outside air temperature drops, air source heat pumps, their capacity drops off. And so what you see here in a graph in orange is sort of how the coefficient performance or the efficiency varies with outside air temperature. And not only does the efficiency vary, but the actual capacity of the equipment varies. And sometimes when it gets really cold, it doesn't work at all. So air source heat pumps can be a challenge for us. And there's all different equipment. Some works better than others. But the green line that you see on this graph is a ground source heat pump or a water source heat pump's efficiency. It's simplified for everyone to, it's oversimplified, but far more efficient to use water source heat pump technology. So today we're going to talk about tapping into the resources that we have in the ground under our feet. Next slide. And another thing that we also have to think about as we think about utilizing heat pumps and going towards electrification is the carbon intensity of our power grid. And that's changing by the day. Grids are greening, but it's important as you do sort of an analysis to understand what makes sense for a project to understand the carbon intensity of the power grid. Because on a really dirty power grid, that air source heat pump, even though it's twice as efficient as an electric heat, it might not be more efficient when you consider how dirty the power grid is. And you might really need to consider water source. Next slide. So in 2015, a little bit maybe before our time, we weren't talking that much about some of these things. SmithGroup had the opportunity to design a corporate headquarters for a water utility called DC Water. And this is just kind of a picture of it. Fully built, it's fully built now. And so today we're going to talk about a little bit on that project and how we took advantage of wastewater heat exchange. So next slide. To give you some context of this building, you can kind of see in this picture in the back the Washington Monument. This site is on the Anacostia River in DC, and this building is actually built on existing land of the water utility, and it's their corporate headquarters. And we're going to talk a little bit about the challenges of the site. Next slide. So what you see here is just sort of a bird's eye view of the site, and the sort of orange shaded area is where we actually put the building, and the red outlined area is just the property of DC Water. And on the next slide, you can see all of the infrastructure, underground infrastructure that is on the site. So not only did we design a building and build a building, but we had to design and build this building over all of this existing functional infrastructure, which was no small challenge, but a challenge we accepted. And it's really important that we credit DC Water for being super willing to innovate and figure out how we could take advantage of the 330 million gallons per day of wastewater pumped beneath the building where this building is built. They wanted to innovate. They wanted to apply industrially utilized technologies that hadn't commonly been utilized in a commercial building. And so they were an important part of our ability to do a building like this. A lot of that existing infrastructure was like clay and brick pipes and tunnels, fragile, that we designed a building to be built over and also tie into. So it was not without a challenge. The two pumps on this site handle 70% of the district's sewage and stormwater. And so it had to remain operational throughout the design. And much of that functionality of the site you can't see when you go on the site. And a lot of that infrastructure was like 100 years old. So actually, it's about this station in particular is about a third of the city's wastewater per day. So next slide. And this is just the temperature of the water in the sewers. It's a really balmy, 62 to 78 degrees across the course of the year. Sometimes it spikes a little colder during like a rainstorm because this is combined sanitary and storm, but a very stable temperature, far more stable in heat to utilize in heat pump technology than outside air temperature, which varies greatly. So it makes a lot of sense, especially in like a climate that needs heat. Next slide. And we would be remiss, and I know we have a lot of architects on the call, if we didn't also talk about, of course, we first designed this building to passively perform as well as it could. So that involved parametric modeling, optimizing daylight, minimizing glare, optimizing heating and cooling demands over the course of a year. So of course we started there before we started to figure out how to serve this building with active systems. Next slide. And here's kind of a cutaway. I actually love this because it really helps you understand the challenge that this building was to build and design. And I'm a mechanical engineer, so I don't even want to get into the complexity of the structural cantilevering that needed to occur to build this building over this active pumping station. But suffice it to say, it was a feat. And then basically just sort of functionally for the system, there's a wet well that holds the wastewater. And we're able to pump that, and I'll get into a little bit into the equipment. later. I have some other diagrams, but all this is kind of happening underneath the building. And then we're just using that wastewater as a heat source or sink, depending on what the building needs over the course of the year. And you can see in the bottom left, there's a little like sort of Energy Star data. So on this building type, I think it's about 207 EUI was like the median energy use intensity. And this building at the site was 26 kBTU per square foot per year, 76 if you include source. So really well performing building in operation now. Next slide. And again, for our architect and developer friends, a really joyful thing that occurs when you use this technology to heat and cool a building is this is the roof. I don't see a condenser farm. I don't see a cooling tower. What I see is an amazing patio that the occupants of this building get to occupy, as well as greenery. So it's not a little thing that sort of outdoor heat rejection equipment goes away. And we can go to the next slide. And then, of course, as a mechanical engineer, this is the stuff that I think is really interesting to look at. So this is, we utilize the Shark system. So this is the system that actually we utilize to take the wastewater and run it through a heat exchanger to provide condenser water, which is like utilizing a fluid. Just like you do in a regular building with a chiller, you'd run that through a cooling tower, but we run it through in this building a heat exchanger to kind of exchange heat with the wastewater. And just as a whole for the building, the mechanical system is a dedicated outside air system. So 100% outside air handling system that delivers air to the spaces according to the ventilation code. And that typically a DOAS system like that also does all the latent cooling, or in other words, taking the water out of the air. And that, so that system, it would usually get you lead points and stuff because it would be providing more ventilation than you actually is actually required by code. So that's great, and uses heat exchange too as well with the energy or with the exhaust air from the space. So it's not inefficient too, and it's increasing ventilation. Then an energy recovery chiller, which is basically just a chiller that can generate hot and chilled water using the refrigeration cycle, extracting and rejecting heat from the fluid that goes through this Shark equipment. Chilled boxes, which are sort of a chilled beam type system with a fan, and they typically don't have latent cooling, so they don't have condensate drains and wet coils and stuff like that in them. They do the sensible cooling, or like sort of the dry part of the cooling. Fan coil units as well. And then this wastewater heat exchanger, which is what I'm really telling you about today. So this wastewater heat exchanger is a heat sink for cooling. So in other words, it takes away heat from the system when we're operating and cooling, and a heat source for heating, so we can extract heat out of the wastewater to provide electrified, very efficient electrified heating. Next slide. And like, you know, to address the elephant in the room, yes, we are using the power of poop to heat and cool this building. I know you all wanted to know. You know, so that prevents, or that provides its challenging, its challenges. I like that people are sending me laughing emojis. So it provides its challenges, right? Because we know it's not just water, there's stuff floating around, whatever. So that has to be considered. There's, and I'll talk a little bit more on the next page, but there's some things that you have to do to make sure you have, you know, water that can flow through a heat exchanger and not clog it. So you do that, you get through the heat exchanger, and then really on the other side, you're just operating typical chiller type equipment that use this as condenser water. So next slide. And then this is just kind of the piece of equipment. So macerators, like what's kind of chopping things up so it can be pumped, and then there's something that separates solids, and then a heat exchanger, and that's what's in this Shark piece of equipment. Next slide. And I think that's it for today, but I'd love to answer questions if anyone has them at the end. We have another person joining to talk, so I'll pass it to him.
Thank you, Nancy. Yeah, I'm Ulrich, and I'm here to tell you more about how we can use our wastewater to get heat in our building. And of course, it's a huge focus in Denmark. There is, like in Illinois, there is very cold in the wintertime. So why not use our water instead of using oil and gas to heat it up all our building? And to understand why we're using a lot of heating pumps and these things in Denmark is we have a central heating on hot water system in all our cities. So for us right now, there is a regulation that have been opened up over the last 2 or 3 years. So it's possible for us now to put in heating pumps. Before 2018-19, there was a regulation that pushed us to use natural gas. So at that time, it was too expensive for us to use the heating pumps and recycle and use the heat from the wastewater. Yeah, next slide, please. So today I'll start telling about, I have 2 cases. One of them is for a city where there is and a wastewater plant that is cleaning for around 385,000 people. The plant is around 38 million gallons per day. And the city is in the small island between the middle of Jutland and Zealand. There's the capital city in Denmark. This is one of the biggest utilities in Denmark. It's not at the same size as Stignik. The water we clean at this plant on a year is what Stignik almost take on a day, or maybe a minute. But you can still do these things. Next slide. And on this slide, you can see I'll not go through all how we clean the wastewater, but I will tell about why we doing this heating pumps after the secondary and the whole process at the wastewater, and why we have a filter on it before we go into the heat exchanger and going into the heat pumps. And the reason for that is all these wipes, rags, condoms, and all these things that's coming into the toilets. And if you not have a very good screening system in your headworks, you will see a lot of these things going through the wastewater plant, and it will end up in our heating pumps, heat exchange, and it will block them. This is the reason we add on this extra filter to be sure we can deliver very clean water to the heating pumps. And as Nancy also told us about, is the water have a very stable temperature, so this is a very good idea to take this water into the heating pumps. So we have it today a cup around 5 and sometimes up to 6, where we get 6 times more heat out of the pump in what we're putting in the power in it. So put 1 kilowatt in it, you will get 6 kilowatt heat out of the system. And in this case, we do it together with the heat utility and the water utility work together about it. Next slide. And this is where we can see some of the facts where these 2 utilities start working close together. So the wastewater plant are running the filters and these things to be sure they can bring clean and perfect water over to the central heating company. And they can deliver up to 20 megawatt of heat out to the customers in Odense, and it's heat to around 5,000 people. Of course, it depends of how warm or cold is outside, but this is a very stable warm. So instead of Odense add on heat from waste factories and other things where they burn all the waste and to make heat out of it, this heating pump can make the base, so it's very easy for the heat utility to turn up and down for the heating pumps. It's a little bit more difficult if you have a huge coal plant or something, is to turn them up and down. This is why we are moving more and more over to the heating pump system. Next slide, please. And here is a small case on a wastewater plant. We have struggled with to find out how to use these heating pumps also only inside the fence at the wastewater plant, so you can use this heat instead of using gas for heating your digesters. It's possible now to use a heating pump and use the heat from the whole process. And this plant is on 5 million gallon, and it's had capacity to clean water for 50,000 people. Next slide, please. And what we do at this plant was we putting in a lot of small hoses around in the bottom of the tank, and we put the concrete on top of it, and then we add on around 20 foot of water in the tank. So here we have 100% stable temperature on this 57 Fahrenheit the whole year round. And we cannot see anything that do something with the bacteria. A lot of people was scared for what we're doing at this plant. They think they will cool the water down and they will not giving us the same capacity at the wastewater plant, but we cannot see the temperature had changed, not at all. And another thing we also do, so when it was very, very cold, we also take the heat out after the blowers. When you compress air, you have a huge energy loss, and this energy loss will heat up the air. So we can take out this hot air from the blowers, and this air is coming out as you also see at the Stickling plant, out in the bottom of the tank, and it will give oxygen to all the bugs in the aeration. And there was the same, a lot of discussion around it. And in the beginning, we have this regulation, so we were not allowed to use this system. We could use it, but then we need to pay a lot of extra fee to use it. For we in Denmark we don't pay the same tax on our energy we're using at a wastewater plant. Then we need to pay this tax back. But they have changed it today, so now the system is running 100% on using the hot air and mix it with the stable heat from the bottom of the tanks. Next slide. And on this slide here, you can see the temperature that is coming in. Is the blue line is the temperature is coming in before the heat exchanger from the blowers, and this is yeah, I'm sorry, but this is in Celsius, but do a calculation. So before it was around this 170 Fahrenheit, and after it was below the 19 Fahrenheit. And when we looked at everything around the wastewater plant, the capacity and what happened in the aeration and in the process, there was no change and see at all. We have turned it on, running with it for months, turn it off and see what happened. We have followed the temperatures in the water and nothing have changed. So it is possible to use this huge amount of hot air also from the wastewater plant. We also have done some tests and a smaller utility where we think, oh, why not take it from the sewer system? We have tried so many different designs on heat exchanger for the sewer system, but we have not found the best way to use it. They will always block. There is a lot of maintaining on it. So I cannot recommend it right now. Otherwise, you need to put a screen in the front of the raw sewer before you go to the heat exchanger. But for the effluent, and it could be also for drinking water, or put it down in the concrete or in the sides on all the process tanks at the wastewater plant. It will be a very easy way to get a good stable temperature into the heating pumps. And it was the last slide from my side, and like the other speakers are really happy to answer if you have any questions at all, or you are more than welcome to contact me. Thank you.
Awesome. Thank you all so much for your presentations. I think this topic is completely fascinating. As someone who's very interested in how kind of the natural world cycles, nutrients and matter through ecological systems. I love that, turning outputs of one system into inputs for another. I love the idea of our urban environments, considering how we might consider or further consider wastewater as a resource here in heat exchange. So I have been taking a look at the Q&A. Thank you all for posting some of your questions. I think our panelists have done a great job of answering a couple of those in there. So if you posted a question and haven't taken a look again, please do take a look and see if your question has been answered. I did want to pull out a couple, and some of these are kind of combinations of things that have been submitted. So I kind of wanted to start by asking all three of you, what would it look like to do this in Chicago specifically? We heard from, Justin with MWRD in particular. What are the opportunities here? And would MWRD allow wastewater heat harvesting from sewers or deep tunnels on sites that are over MWRD infrastructure? So sort of combining, the project that Nancy did with the utility, and just speaking more broadly about what this could look like in Chicago and what you see are maybe one specific opportunity in Chicago for this technology.
Yeah, not only would we conceivably allow it, we are currently harvesting heat from the wastewater entering our Kirie Water Reclamation Plant. So those of you who attended the tour yesterday, you were able to sit in a room that was being actively heated using the sewage flowing into the plant. But regarding working with outside entities, so that's within our own facilities. Regarding working with an outside entity, that's obviously something that would be above my pay grade to make that call, but it's certainly something I imagine if it didn't disrupt our operations. So our main priority is to get that water through the system and to our facilities. So if there's a way to make it work that wouldn't disrupt things, I imagine we would be receptive to that.
I would just say, I think that, that would have to go through the city too. And so I think part of like our chat, and I'm not saying it's not possible, but I think we need to spread the message of the opportunity and, kind of get buy-in from the various permit officials in Chicago and the plumbers union, et cetera. Like, I do think there's some buy-in required, and it's really important that we as a community and proponents of this, work to kind of get our people on board. And I know years past, I was involved in the design of the new plumbers union building, and I felt like they were really incorporating some innovative and newer technologies, so that they could have their workforce development be learning new systems. So to me, it feels like that landscape is open to that. And also, but I personally, I'm not an expert. I haven't tried to implement it in Chicago. So I think all of us as designers, developers, people in the built environment community, need to push for this as an opportunity, need to kind of look at our project sites and understand what is available there and really innovate.
Yeah, and from my side, I think it'd be very difficult. I'll not say it's not possible to do in Chicago, but if you don't have the central heating, it will be very, very expensive, and your payback time will be crazy high. But
if you don't have what, Ulrich?
If you don't have the central heating, you have the hot water pipes around in the city. It can be difficult to get the heat out to people. Otherwise, you need to do it only heating pumps per buildings if you do it with hot water.
Right, but we have cooling requirements too, so I mean, it's a natural fit to have that equipment inside a building.
Yeah.
It's very viable.
I wanted to follow up sort of, I think Nancy, you had mentioned in somebody's question asked, does this design make the energy for the facility carbon neutral? And you said it would have to be fully served by decarbonized power to be considered carbon neutral. So I kind of, that question also made me think about, in your case for DC Water, and then I'd love to hear from the other panelists too for their case studies, but what were the goals that motivated the utility to do the project in the first place? Was it about energy saving? What were the motivations behind getting these done? Because as you mentioned, that project looked quite challenging and probably expensive to pull off. And so I'm just curious if we're going to be advocating for this in other areas, what has been motivating factors for these case studies?
Well, I mean, I think decarbonization, I mean, that project was just a natural fit, like all the planets aligned. But I will say, like, they just recently put out an RFI in DC. They have centralized systems serving 60 federal buildings, and they are giving tours of DC Water and tours of their centralized plant in DC. And they're asking for ideas from designers and utility leaders on how to decarbonize their systems. And they also have identified where they have like sewer mains along the, in the city near these buildings. So I guess, I mean, we just have to think in that way, like, what are the opportunities, right? And I think not to derail the sewer heat exchange, but there's other opportunities for for water exchange, could be rivers, could be like anything really big, like the lake, any really big stable source of stable temperature water is, and then also including geothermal boreholes, like all of these things kind of meet the same ideal condition scenario for efficient electrification in a cold climate like Chicago.
Yeah, and I think for the city of Odense, it was, of course, what happened here right now. Our oil, gas prices is rising a lot. So for them and to be and have a stable heat for the city, will be the easiest and most safe way to go with the heating pumps. And for the wastewater plant, the smaller one, it was a plant they want to build from scratch, and then said, okay, why not go in and do a green solution when everything is open up?
In our case with our Kirie plant, it's a pilot project, but it's something that we implemented as part of our broader effort to reduce our carbon footprint in our operations. One way that we're looking at doing that.
Great. Thank you, guys. I think we've sort of touched on this, but I'd love to just see if there's anything else to flesh this out a little more. Would these types of heating systems work well for district heating plants, a system that services multiple and connected systems? And I think we sort of touched on that, but just if we could speak a little bit more to any thoughts you have on scaling this.
I mean, I think a lot about our centralized chill water that we have in Chicago. And could we repurpose that water that's already piped under our streets to be more of an ambient loop to work with heat pumps? But the challenge of that is that we have buildings in place and they are depending on that, and they would require changes inside them about what systems they could use. So we need like all the smart people at the table to think through how we can do these things and how we can phase them over time, right? Because nobody can do everything all at once. So like, what are the options? Which is exactly the spirit of that DC RFI, request for information. It's like, I want everyone's best ideas. How can we get there? And I know through the Department of Energy's Better Climate Challenge, we're dealing with this with partners and end users across all markets, campuses, higher education, healthcare facilities. how can we get there? You know, we know that 80% of the buildings that are going to be here in 2050 already exist and already have systems. So the biggest challenge, the new buildings, we should be doing these things right now. But the buildings that are already there, how can we think through how to implement this with the practical considerations of what's here now and how we need to still operate? Unfortunately, there's not like a simple answer to all of it, but we all need to like push the boundary and ask why. And I also think there's a historic change to the funding landscape, at least for the moment, and Inflation Reduction Act incentives that helps pay for a lot of this. Someone gave me a heart emoji.
Ulrich or Justin, anything to add?
No, it's don't have anything to add it for. This is the way to do it.
Okay, I'm curious about this one. Well, I should also say it's 12:56. I'm not going to get to all of these questions. I believe we can work with the panelists to get any answers out to folks. We can email them out afterwards. Twyla, am I on track with that comment?
Yeah, absolutely.
Okay, great. So if your question did not get answered fully today, we will follow up. But I just had two, if we could, the Kirie tour made it sound as though there isn't always enough water in the sewers to keep things flowing. Would you say that most of the service area of the MWRD has enough flow to run pipes for heat pumps through the sewers?
Yeah, possible. Kirie is a sort of an unusual setup. Not to get too into the weeds, but we also have what's called the deep tunnel system. Kirie is connected directly to that deep tunnel system and is designed to have pretty wide fluctuations in flow when we're dewatering. Our other plants like Stickney is so much bigger and gets so much more water coming through that I imagine it could be a more dependable source of lots of water moving through.
Great.
I
Let's
think
see.
the other thing is you can have a tank, but I know we're almost out of time, but you can have a tank too. So like if you don't have things flowing constantly every minute, you can have a tank that is getting regenerated over time.
There was a question about, given Chicago's ecosystem, we have the lake as a potential water source. How about the 33-degree river water? Is that too cold?
Well, I just think, I mean, there's constraints on what equipment can do, but if the water can flow, likely there's a solution that can allow heat pumps.
You got to get a permit for that, though. That's one thing. Like
That's right.
our effluent permits, we have a temperature. Temperature is one of the things that the state looks at if you're discharging. So you can only.
In Chicago, there's all kinds of buildings that are extracting water from the river right now, but you're right, Army Corps of Engineer permit. So I think they're kind of grandfathered.
Okay, great. There were a couple other questions about treating water at through MWRD. I thought, and there's another comment on here about just how we can continue to think about co-locating PVs on these types of properties. So just a lot to consider about how all of these things work together, these complex systems. And I just want to thank you all again for your thoughtfulness and great and interesting presentations.
Yeah, thank you all. Thank you, speakers. Thank you, everyone who joined in to listen. We will be sending a recording of this webinar out to you all, and we'll try to get our speakers to answer a few more of those questions online and send those out to you in the follow-up email next week. Speakers, thank you again. Everyone have a great afternoon and try to stay warm out there. Have a good one, everybody.
Thank you.
Bye.
Thank you.
Care.